We move on to question 6, which reads as follows. 27 standard dice are arranged in a 3 by 3 by 3 cube. The diagram is given there, as you can see. What is the probability that at least one die shows a 3 on the surface of the cube? Write your answer in terms of an irreducible fraction of powers of prime numbers. All right, so the question is now, what is the probability that in all these 6 faces, there are 6 of them in a cube, there is at least one 3? All right, to tackle this problem, it might be easier to work out the probability that 3 does not occur at all. Right? So either 3 does not occur at all, or at least one 3 appears on the surface of this cube. Okay, so you got the probability of at least one 3 plus the probability of no 3 is equal to 1. Either there is no 3 does not appear at all, or 3 appears at least once. And these are the only 2 possibilities. So the sum of these 2 probabilities will be 1. Probability of 1 means it always occurs, that probability. 0 means it never occurs. Okay, so one of these definitely always occurs. Okay, so let's work out the probability of no 3. Okay, so it means that none of these faces has a 3 in it. Now, there are 9 sides of a cube on each of these faces. So there are 54, there are 6 faces altogether. So there's 54 such faces. It would appear that, I'm talking about the faces of the dice or the die. So it would appear that each one, the probability is 1/6 for a 3 to appear. So we have to work out the probability that 3 does not appear. All right, now one has to be a little bit careful here. You see, on each face there are 3 types of situations. You got the corners. In this diagram here, the corners is depicted by A. And you got the middle, which is depicted by C. And then these 2, there are 4 of them, shown by B. Now, we need to work out what is the probability that 3 is not on one of these faces. So let's take the A face. Right, 3 is not on any. Corner. Now, that means 3 is inside. There are 3 other faces in this cube here that I'm pointing to. It's a corner cube. And the probability that 3 is not on this means that the probability that the 3 is on the other side. And that probability is half. Probability that 3 does not appear is 3/6. It means it appears on the side which you can't see. And if you apply this now to all the corners, there are 4 corners at the top and 4 corners at the bottom. So the 4 A's at the top, 4 A's, so there are 8 A's altogether, right? And here, therefore, when you take A, I'm not writing it out in full. When you take A, the probability is a half to the power of 6. At each corner, the probability the 3 does not appear is a half. And there are 8 such corners, so you multiply all the different probabilities on that. Okay, so now let's look at B. The B cube is like this one here. But the B cube, there are only 2 faces which are exposed. Right? These 2. That means the 3 is on the other side. In this case, 3 appears on 4 of the 6s. Six faces of each die. This is the B die. Right? Therefore, in the B case, 4 out of 6 means 2 out of 3. 2/3. And how many faces do you have like that? You got 4 on each slice. At the top, you got 4. In the middle, you got 4, those 2. Oh, wait a minute. You got 4 at the top. And then, yeah, in the middle, you got another 4. These 2 here, those 2 there. And in the bottom, you got those 4. This thing to the other side, and on the opposite face to this. Now, 12 faces where only 2 sides are exposed. Right? That's what we are saying. So it's 2/3 to the power of 12. And the C face, that's the middle one. Now there, the 3, we are saying the 3 does not appear on this flat face here. So there are 5 faces which are not exposed. Only one of these is exposed. So the 3 occurs in 5 of those faces. So the probability that it occurs on 5 of the other faces is 5/6. And there we have, how many such middle faces have you got? Okay, there are 6 faces of the cube, and each face has got one middle face. So it's, so yeah, I'm counting here, 6, 12, 18. We have taken care of 24 of these faces. And if you count the number of exposed faces, you will see that there are indeed 24. 9 at the top, 9 at the bottom. That makes 18. And then uh, this is 8 here. There are 8. 8 corners. All right. And if you add them up, you get 26. And there are 27 altogether. So the one which has not been dealt with is the one right in the middle, right? Which is, there's one cube which is hidden inside the solid cube. So the answer is the product of all these probabilities, and so half to the 8 multiplied by 2/3 to the power of 12 multiplied by 5/6 to the power of 6. Okay, no, this is not the answer. This is the probability that 3 does not occur. So so for the probability that 3 does occur is 1 minus, because the sum of these two probabilities is 1. So that's the answer. So it's 1 minus, and if you multiply all these things out, they ask you to, in terms of an irreducible fraction of powers of primes, let's just do that. Then the product of 3 fractions like that is what? The numerator is 1 to the 8, 2 to the 12, 2 to the power of 12, 5 to the power of 6. At the bottom, you got 2 to the power of 8, 3 to the power of 12. You got 6 to the power of 6, which is 2 to the power of 6, times 3 to the power of 6. Okay, so these are your prime factors. And 2 to the power of 8 at the bottom, 2 to the 8 plus 6 is 14. So you have 1 over 2 squared. Denominator, you have 2 squared. Numerator, you got 5 to the power of 6. And the 3 is 3 to the 18. Okay, you really can't answer this question. This is not an irreducible fraction, but it's very difficult to factorize this huge number here. If you take this number and subtract 5 to the power of 6 and try to factorize it, you're going to get into trouble. So I think this is the answer. Let's just check it. I may be wrong. It's 1 minus 5 to the power of 6 over 2 to the power of 6 times 3 to the 18. Okay, we're going into this. Yeah, exactly. It's 2 to the 2 squared, because you have 2 to the power of 14 and 2 to the 12 at the top. So the denominator is 2 squared. You can see the answer right at the bottom. Okay, so that takes care of question number 6. We now move on to question 7. So here's question 7. Question 7 says, given a triangle ABC, 3 lines passing through the point O and parallel to the sides cut the triangle in 6 pieces. All right, so let's just have a look at which lines are parallel. Okay, so you got this line is parallel to this, and this line here is parallel to this. And there's one other line, this one here, is parallel to that. Okay, so you have a number of similar triangles here. So what's the question? 3 of these pieces are triangles whose areas are 9, 12, and 9, 16, and 25. So the smallest one has got area 9, and another one got 16. These are the areas, right? And they ask you to find the area of the entire triangle. Okay. Now, we just want to see, you see, these triangles are similar. If you take this one here and this one, they're similar. And when you have two triangles that are similar, then the ratio of their areas is a square of the ratio of the scale factor. Let me explain that. Okay, I just want to write this down. So what I've got here is there's a claim here that we are making that if you got a triangle, sorry, the writing is very small, uh, like this, and you got one side, two sides, two line segments that are parallel to the sides, as you can see, then if this area is a squared and this area is b squared, then I'm claiming that this implies that this area here is 2ab. Right. Now, this is a claim. We're going to try to prove this. But before we do that, I just want to talk about similar triangles. If triangle, say, ABC is similar to triangle XYZ, that means that the sides are in the same ratio. Let's call it K. AB over XY, BC over YZ. See, as long as these have been named in a proper way, angle A and angle X are the same, angle B and angle Y are the same, angle C and angle Z are the same. If you name it like that, then these sides are first second over first second, second third over second third, and then first third over 1 3 over 1 3. Okay, and this is the common thing. Then it means that the triangle ABC, its area is equal to k squared times area of XYZ. All right, so this the ratio, what we have got here is the area over this area here. So in other words, the area of one over the other is k squared. Okay, so now here you got this area is a squared and this area is b squared, and these two triangles are similar because you got a parallel line. Whenever you got a triangle and you got a line parallel, a line segment is parallel to one of the sides, then you got these small triangle, this triangle here, always similar to the large triangle because these are corresponding angles are equal. You can check it out. All right. So what it means is that you got the square, this triangle area over this triangle as we got is k squared. So it's b over a now, you see. Your k in this case is b over a. All right. So you'll have that if this is K, this is BK. I'm sorry. If this is B, B is equal to AK. So if this is B is AK. All right, so this is the ratio. This over this is is K. In other words, this side over this side is K, that side over that side is K, that side over that side is K. The ratio of the sides is all equal to K. All right. So let's try to prove this statement here. Uh, so what we have here is I'm going to look at this triangle over the large triangle. And this small triangle is similar to the large triangle. I'm not going to compare these two. I'm going to take this triangle here to the large triangle. So what do you have? Yeah. So you got, this is AK, this is BK. And let's not worry about the symbols that are used in the proof of this. What we are saying here is that the ratio of the sides is K. So is A over B. See, this area is A squared, and this is B squared. Okay, so therefore, the ratio of this is to this is A over B. So you can make this KA and KB. All right. Let's take that out. That's confusing. So now, if you take the area of the small triangle, say A squared, that's that area, over the area of the entire, okay, we don't know what this is. Let's call it X. Area of the entire triangle. So this area over the area of the entire triangle, this area, the area of this parallelogram is X, is the same as the ratios of the sides squared. So this side here, if you call it B, or A at least, and this entire side will be A plus B. That's the ratio we got. This over the entire thing, you got AK over AK plus BK. And this over that is a ratio of the sides of these two triangles. The k's cancel, and you have A over A plus B. So this is your K, which is K squared. If you simplify this, you got A squared plus A squared plus B squared plus 2AB. And the middle term is 2AB. So you can see if you compare these two things, you'll have to see that X must be 2AB for that equation to be true. So that's how we say that this area of this parallelogram is actually 2AB. Okay, I'm sure that should be quite clear. Now we want to go on. I just want to go to the actual problem at hand. We're going to apply this result. What we had here was, they said this is 9, which is 3 squared, and this is 16, which is 4 squared, and this 25. So let's look at the triangle, which has got these 3 as vertices. Right? So you got exactly what we've got before, but it's slightly different. But you've got two sides, 2 line segments are parallel to the sides. And we saw that the area of the parallelogram is 2AB. But this is A is 3 squared. This is 4 squared. So this is 2 times 3 times 4, which is 24. Right, so you can work out the area of this parallelogram. Here, in this case here, you got this triangle, you got 25, 16. So this is 2 times 5 times 4. 5 squared, 4 squared, 2AB would be 40. So the area of that parallelogram is 40 and this is 24. And likewise, this one here will be 30. 5 times 3 times 2. So the area of the triangle now is just a sum of the areas of all these. And the answer is, you can work out, add up all these things, and I think you get 144. Okay, so that's the answer to this problem. Okay, so that takes us now to question. Well, let's just see. So there it is, right at the bottom. You're 144. All right. So this is the the solution that I worked out before coming to this class, and it's the same as what we just came to. Okay. So now the next question is this question 8. Question 8 says a set of knobs. Okay, I'm not going to read this long essay here. I'll tell you what this question is saying. You got a knob, right? You can turn this thing here anti-clockwise, or you can turn it clockwise or anti-clockwise through 90 degrees. So then you have this arrow. It could be pointing like this when you turn it through 90 degrees in the clockwise direction. The other way can be played like that. So you can turn it in both, any one of them. And this is some kind of a panel where you're probably trying to put a code there and lock it up, right? So what the person does is they just turn these things in a random way, and it'll be very difficult to come back to the original one. Okay, now what they are saying here in this problem is that when you turn it like this, you have these arrowheads. I'm going to write the arrowheads like this. Right? So you may have a situation like this. Suppose it's a set of knobs. You don't know how many there are. So, and in the end, the question is how many knobs are on the control panel. So I'm going to say that n be equal to the number of knobs on the control panel. Okay, so here you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is 10. Because each of these 10 knobs have been turned in one particular direction. Okay, now this question says that some of these arrowheads point at the arrowheads. Like here you can see this arrowheads, it points like this arrowhead points to this arrowhead. And they're all facing each other. Here too. Some of them arrowheads point to the arrowheads, as we got here, and others, and some at the arrow tails of their neighbors. So this points to the arrow tail of his neighbor, right? Not this one. Here, but here too, you got this points to the arrow tail of his neighbor. See, in this case here. All right. It is found that the total number of arrowheads pointing at arrow tails is 6 times the number of arrowheads pointing at arrowheads. All right. What I'm going to do is I'm going to code this thing. If an arrow is pointing to the right, I'm going to call it right. This is pointing to the right. So I'll describe, oh no, this one here is L, because this arrow here points to the left-hand side now. L, so right, left, right, left, right. Okay. Now, it says here the sum of the anti-clockwise and some of the right clockwise. Yeah, some of the arrowheads point to arrowheads and others to elsewhere. Let's look at the different situations you have. There are 4 types. 4 types of neighbors. You got RR. That means both these neighbors, the arrow is pointing in the right. Or you could have LL, like this case here. Or you could have had LR or RL. Right, so that's what we got. And I want to count how many arrows point to the tail of the others, because there's something said about that. So the number of arrows that point toward the tail, the RR ones, suppose there are ARR ones. Right? Now A is equal to 1 here, I think. There's only one RR. Now wait a minute, there are 2. There are 2 RRs. And then the LLs, you got 1. Okay, there's only 1 LL. LR, you got 1, 2, 3. You got 3 LRs. And RL, you got 1, 2, 3. All right. So if you count all these different types, you got 3, 6, 9. It's 1 less than 10. The reason is that you got 10, but there are only so many gaps in between, so many pairs leading from left to the right. Okay. So in this problem here, you got that situation. I'm going to give a name to this. I'm going to say A is equal to B is equal to this, C is equal to this. So in other words, we got small a RRs, small b LLs, small c LRs, small d RLs. Okay, I need space and I can go into the next. So n is equal to the number of knobs. Okay, let me leave all these things. I might need this. So what we've got here is you got ARR, BLL, and you got CLR and DRL. Okay, and of course you'll have that A plus B plus C plus D. We saw there were 9 here. It's one short of 10. This gives you the number of pairs. If the n, this will be n minus 1, as we had 10 and 10 minus 1. Okay, at least we got an equation. Right? The question is how many knobs? Right? How many knobs do you have? But they give you some information. Let's have a look at this information again. Right, it says that some of the arrowheads point at the arrowheads and some. Right, now, the next statement. It is found that the total number of arrowheads pointing at arrow tails. Now, the arrowheads which points at arrow tails are the RR ones, arrowheads pointing to arrow tails, and the LL. Yeah, these also, the LLs also, the heads point towards the tails. So this number here is equal to 6 times the number of arrowheads pointing at arrow tails. Now this is an arrowhead pointing to an arrow tail. So it's 6 times RL. Right. LR, you don't have an arrowhead pointing to, they are pointing opposite each other, away from each other. But here, the number of arrowheads which are pointing towards arrow tails, right? This is an example. Okay. So you got, now how many R's are there? There are A of these. So A plus B, total number here, is equal to 6 times, and we said RL was D. Okay, I'm going to put this down as an equation. A plus B is equal to 6D. A plus B. Right. Now, the question goes on to say the following. The knobs now, they are now turned again, this time through 180 degrees. All right, in other words, if it's pointing to the left, like this, you turn it 180 degrees, which is the same as if you have an arrow pointing like this, then you turn it around 180 degrees, it changes. The L changes to R, and the R changes to L. Right? Now, this time when you do that, now the number of arrowheads pointing at the arrow tails is 7 times the number of arrowheads pointing to. Right. So let's just have a look at that. If you look at our example here, you will see that So if you turn every one of these through 180 degrees, then what happens is the R becomes an L, the L becomes an R, right? And this time, the number of arrowheads, now you have the, because the R's become L's, the number of these R's switch to that and the L's switch to that. So you will have in this new configuration, the A becomes B and the B becomes A. So again, you have that A plus, it's the same thing. A plus B is the number of R's plus the number of L's. The only thing is you don't have A plus B here, you have B plus A, right? Which is the same as A plus B. Okay, so this number here is now 7 times the number of arrow tails, 7 times what we had before. See? Like the RLs here is 1, 2, 3. So RLs is the same, RL is 3. So you'll notice that even in this new situation, RLs are 3, and LR is LR, LR, LR. That's also 3. So you'll notice that the RLs is the same as the LRs in this case. Now there's a let's write that equation down. So the C now becomes D, because RL becomes LRs. So in this case here you have that A plus B, this is LL plus RR, right, is equal to, now the RLs become the 6 times RR, this becomes LR. So this is 6C, LR is C. So you got those, so you got these 3 equations. And the problem is to find N. Oh, I'm sorry, this is 7. It turned out that this is 7. Not the same. Now, let's just find a connection between this RL and LR. You see, the number of LRs, yeah, you see they're both equal. LR and C is equal to D in this case, right? But there could be a situation when it's not like that. I could have had LR, 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 for instance, right? Here, C is LR, C is 3, but RL is 2. RL, RL. So you need not have the C is equal to D, but you could have the C is 1 more than D. In fact, this always happens. You see, if you have a number of L's and then you suddenly switch to an R, then you go to L. Each time you go from L to R, the moment this pattern switches, it'll be from R to L. So it'll be like that. But there are some cases where the number of C's is, you've got 2 RLs between one L and R. In that case, you will have 2 LRs, RLs, and 3 LRs. Right? So the point is that C equals D, or C minus 1 equals D, or D minus 1 equals C. To differ, C and differ by just by 1. I should say C minus D equals 1, or D minus C equals 1, right? Depending on which is bigger. Okay, let's have a look at these three equations. I can replace the D by A plus B over 6. Okay, the C here in this equation, I can make it A plus B over 7. And the D in this equation, I can make it A plus B over 6. Right? And that is equal to n minus 1. Okay, now you can see I can take out A plus B as a common factor in that equation. A plus B times 1 times 1 over 7, 1 over 6 is equal to n minus 1. And when you take that fraction and simplify it, you get a common denominator of 42. So here you have 42 plus 6 plus 7 equal to n minus 1. And this gives you 48 plus 7 is 55. Okay, so you get A plus B into 55 over 42 equals n minus 1. So n is equal to oh yeah, I made a mistake here. Um, Sorry about this. You see, when you have a thing like this, right? When we say when we're counting the number of arrow heads pointing to the arrow heads on the other side, this way you're going to count 1 here, and you're going to count 1 here again, because this is pointing to this side. See, so this is your RL. The RL is actually, you have to count it twice. It's not C, because the number of situations where the head is pointing towards L, whenever you have an RL, you have to count twice, 2 times. You count it here. This is where this arrow is pointing to the head, and this one here is also pointing to the head. So you have to, each time you come to you take each arrow and find out what it's doing. You'll have to count this twice. So what you've got here is actually you're supposed to have 12 here, right? The D RL is not 6 but 12. And the other one will be 14. Okay, this number is not 6, it's actually 12. So D is equal to A plus B over 12. All right, so in that case, you've got over 14, and you got 12, you got 14, 12. So this time you got A plus B. Now, when you work out 1 plus 1 over 14 plus 1 over 12 plus 1 over 12, the common denominator here is 84. So you get 84. 14 goes into 84 6 times. 12 goes into the 7 times. So you have 84 plus 6 is 97 over 84. All right, so this expression here, let's take this, no, this is wrong. That thing there becomes 97 over 84 equals n minus 1. So this tells you something. See, this a plus b, this is an integer here. It counts the number of knobs. So for this thing to work, you must have that a is integer, b is integer. They count, there's a certain counting number. But to make this thing an integer, it means that a plus b must be 84. Therefore, a plus b is equal to 84. Or in fact, it could be any multiple of 84. Maybe 2 times 84 or 3 times 84. Some multiple of 84. For this thing, you have to be an integer. So let's write that down like that, and we say a plus b is equal to 84 times, say, k, where k is an integer, a positive integer. Can't be 0 because a plus b can't be 0. You see, if a plus b is 0, and I want to say it's a positive integer, then you'll have n is equal to 1. It means you have just one arrow. And it says there in the question, some of them are turned left and so on. So there's more than one. It's a subtle reference to the number in that it says at least one, at least 2. Okay, so you got this. Now, where are we now? How does this help us? So therefore, you got D is equal to A plus B over 12. A plus B is 84K. So if you divide that by 12, you get 7K. And C is equal to A plus B over 14. There. So there you get 84K over 14. That gives 6K. And you'll see that D minus C is equal to K. 7K minus 6K. But we said earlier on the D minus C, right, the difference between the RLs and the LRs is either 1 or 0. So this is equal to 0 or 1. Right? Now K can't be 0 because if K is 0, then A plus B is 0. And D is also equal to 0. C is equal to 0. Everything is 0. So what happens is that N is equal to 1 in that case. See, if A plus B is 0, then n is equal to 1. Okay, this is out. So k is equal to 1. Okay, so we needed to find out what n was. So n minus 1 is equal to, as we saw, it's so if k is equal to 1, this equation here means a plus b is 84. So a plus b is 84. K is equal to 1. You see, there's k equals 2 here. Okay, and if a plus b is 84, then it means that n minus 1, this is a plus b is 84. So it's 84 into 97 over 84. And 97, n minus 1 is 97. So n is 98. A very unexpected answer. N is 98. All right. So I actually nearly got it wrong because I didn't count the LRs twice. Okay, so let's just clear the next. We said the answer is 98. Or right at the bottom, you can see n is equal to 98. And there's your full argument. So if you didn't understand what I said, you can read through this page, freeze it, read it, and try to make some sense of it. Okay, now we get on to the next problem. Question 9. It says in a regular hexagon, A, B, C, D, E, F, all the sides are equal, all the angles are equal. It's a very popular figure, a regular hexagon, just like the square. The square is a regular quadrilateral. All the sides and all the angles are equal. And it's got a lot of applications. And even this to the regular hexagon. I think beehives and all that are made of regular hexagons. They appear in nature. There's a straight line passing through B, as you can see. There's B here. And this straight line which goes through B, it cuts AC and it cuts EC at M and N. And they say that ratio AM over AC, AM over AC, or the whole thing, is X. And CN over CE is also equal to X. Right? And the question is find the value of X. Now, this is not an easy problem. It took me a long time to, I couldn't do it. And I had to look at the solution. Even then, it took me a bit of time to understand it. So I'm going to try to explain to you. This is a very nice geometry problem. Hmm. Oh, mm. Okay, let me, this is the solution. Uh, I don't want this. Let me get out of this. Okay, I'm sorry. I should have just drawn that diagram just like that on a blank page. Uh, now, why did this thing come on here? All right, okay. Okay, so I got my blank page. Um, no, unfortunately, I did draw this thing recently. Okay, let's not worry about that. I wanted to just talk about the properties of a hexagon, a regular hexagon, and it's I had drawn this in advance, but now I can't get it, unfortunately. So let's redraw this thing. I'm not going to be. I drew a very accurate picture. Now, the thing about any regular picture, whether it's a regular polygon or a regular hexagon or a pentagon and so on, there's a very important fact associated with it, and that is all those points lie on a circle. You see, all the vertices lie on a circle. So let's just get. I'm going to draw this thing inside the circle. Then it becomes more obvious. See, all the 6 points lie in a circle. So you got the center, and then you have 6 equilateral triangles. That's how you draw an hexagon. I'll show you. So you draw a diameter, and then you divide this into 3 equal parts. Draw another diameter, and then draw a third diameter. Like that, and make all these angles 60 degrees. And the endpoints, so there you have your hexagon. See, so that's how you make a regular hexagon. And there are 6 equilateral triangles here. So there are a lot of interesting things that happens here. You can see, like for instance, uh, one diagonal looks like this, and like that one, the short diagonal. Then you got a secondary diagonal like this kind of a diagonal. And then you got the third diagonal, which goes from one opposite to the other. The third diagonal, the longest one, is also the diameter of the circle, right? And because this is an equilateral triangle, this is the center of the circle. So you have these are radii, and you got 60 degrees here. So it means that these 6 triangles are all equilateral triangles. But you'll notice that the side of the hexagon is half the side of the longest diagonal. because the longest diagonal is the diameter, and the side of the hexagon is just the radius of the circumscribed circle. So that's useful also, that the side of the hexagon is half the side of the longest diagonal. Okay, and then you have like this becomes a rhombus here. You was going to try to analyze the properties of a hexagon. Another one is if I join these other diagonals, in other words, I join the alternate vertices. This, avoid that, join, avoid, join. Then this part here, this inside part, becomes an equilateral triangle. It becomes an equilateral triangle. And the reason for that is, you see, the best reason, the easiest reason is that all the angles of your original hexagon are all equal. It turns out they're all equal to 120 degrees. As you can see, there'll be 260 degrees here. So the interior angles are all 120. All the angles are equal. And then you will see that this chord here subtends 120 degrees, and equal chords subtend equal angles. And conversely, equal angles are subtended by equal chords. So you will have that this chord here is subtended by 120 degrees, must be equal to this one here. And even this will be all equal. For the same reason, they all subtend 120 degrees, so you got an equilateral triangle in between. Yeah. So this big picture has got lots of interesting properties. Just bear all that in mind, because I'm not going to write down all these pieces of information, but we're going to use them along the way. Oh, by the way, one of the angles is 90 degrees. You've got a rectangle sitting inside here. You see, this is 100. This angle here is 120 degrees, as we said. So this is an isosceles triangle, a small fellow here. So these two angles add up to 60 degrees. So each of them is 30. So the sides of the hexagon subtend 30 degrees at the circumference. Bearing in mind that equal sides, equal chords subtend equal angles, lots of 30 degrees in this picture, right? Because every side will subtend 30 degrees at the circumference. If that is 30, and we saw that this is 60, right? So you have a right angle here. In any case, if this is 30, the whole thing is 120. You got a right angle. So you got a rectangle here also. See? Many ways of viewing this. You see, you can also view it like this, that when you go directly across, you got a diameter. The diameter subtends 90 degrees. So that is 90, that is 90. And if you take the other diameter, yeah, then you got the other two angles at 90 degrees. So this becomes a rectangle. So the rectangle in this picture, there's the rhombus, the equilateral triangles. Very interesting. And then you also have trapeziums, isosceles trapeziums. Okay. So let's bear all that in mind. And I'm just going to wipe all the insides. So in our picture, the actual problem, we had that this line here was joined. Oh, let me make this black. And this line was joined. And then you have from this point here, you have something that goes down and cuts X. Right? And we had a ratio. I'm going to say, let's use the same symbols that the question had. The question had A, this is A, B, C, D, E, F. Let's see. A, B, C, D, E, F. All right, so you've got C, E, and B, M, N. Good. A, B. I want to name this in the same way as I named in the question. So I'm going through all this because I forgot to draw the diagram. Sorry about this. So this is B, this is M, this is N, this is A, B, C, D, E, F. All right, and it was given. Now I'm going to say let AC be equal to X, AC be equal to 1. In a geometry picture, you can always take any one particular line and you can call it 1, but don't, that's it. The rest of it, you'll have to name it according to that 1. Right? If it's half the length, you must name the half, and so on. Right? To simplify calculations, we do that kind of thing. So AC is equal to 1. Remember, I told you that this is an equilateral triangle. If AC is equal to 1, this is also equal to 1. Right? And we said that Cn over 1 is equal to AM over 1. So this is X there, and this is X here. Right? And that was the thing that you needed to calculate. AM over AC, I think we had, is X. But if I call this AC1, then this becomes X by itself. Okay, now we need to calculate this. Now to do this, let me first, I didn't have to color that red. Okay. Now, the idea is to actually complete this rectangle. I'm going to put this in color because this is a construction. Now you see, this becomes a rectangle here. Right? We said that the reason for that is that this B, E, and the other one becomes their diameters. And diameters of circles subtend 90 degrees at the circumference. Right? These are all properties of a regular hexagon. All right. Now, also, let me just join this as well. Right. Now, remember, this angle here is 90 degrees. See, FC becomes the diameter of the circle. In the actual question, there was no circle. I'm drawing the circle because I know that in a regular hexagon there is a circle. So that too is a construction, right, around the circle. Okay, now remember we said that this becomes the radius. So and this so there's a certain ratio here. This AF is also the radius of the circle. In fact, all these sides outside are all radii of the circle. Because right at the beginning, I told you you got all equilateral triangles. So you've got from the center, if you join it to the vertices, all these three are equal. So the sides of your hexagon are equal to the radius of the circle. And this is the diameter. So AB over FC is equal to a half. AB over FC, because AB is the radius and this is the diameter. All the sides can be regarded as radii. Okay, so that's an important conclusion here. And then also, this AB is parallel to FC. What's the reason for that? AF subtends 30 degrees. I told you earlier on. Well, whatever it is, it subtends equal sides subtend equal angles. So BC subtends that angle, and all these sides are equal. So equal sides subtend equal angles at circumference. So these two angles are equal. So therefore, but these are alternate angles. So those two lines are actually parallel. Because you've got a pair of alternate angles are actually equal. All right. Now, once you got that is parallel, then now you got a lot of similar triangles. See, in the hexagon, you even got some similar triangles. Now, let me just take this x out for a moment. Just remember that x was AM. This length here from here to here was x. Uh, 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 I'm going to call this intersection point L. Now I got these two lines are parallel. So you got this triangle ALB. ALB is similar to, let's take CLF. The angle A was equal to angle C, and B was equal to this. So you have to put the B and the F at the same place. Both go at the ends. All right. Now, which means that AL over LC is the same as AB over FC, right? So, but we saw that AB over FC is a half. AB is a half of FC. So it means that AL, this triangle here is similar to CLF. AL is half of LC, right? Now, you've got AC was equal to 1. We said in the beginning that we let all these sides of this equilateral triangle be equal to 1. And then you got AL is to LC as 1 is to 2. It's a half. But the whole thing is 1. So, therefore, AL will have to be 1/3. See, AL will have to be 1/3. And LC will have to be 2/3 because LC is twice AL. Okay? Now, remember, AM is X. I told you to remember that. So this part here is 1 minus X. So AM is X. Oh yeah, AM is X. So therefore LM is X minus a third. LM, because AM is X, right? I rubbed it out earlier on. So that part is 1/3. So LM is X minus a third. Now look at MC. MC, the whole thing is 1. AM is X. So therefore, MC is 1 minus X. Because the whole thing is 1 and AM is 1 X. So you got that. Now, if this is 1/3, so is this. Because you've got equal chords subtend equal angles of the circumference. So therefore, this one here becomes an isosceles triangle. If that is 1/3, this is also 1/3. And this part here is X. Now, something magical happens here. Because we see that this line is parallel. You see, BF is parallel to this because this is a rectangle, right? So you have another pair of parallel lines, and you have that triangle is similar to those two shaded. Those two shaded triangles are similar because you got a parallel lines and you got these angles are alternate angles and so on, vertically opposite angles. So these two triangles are similar. So the sides are in the same proportion. But now I wrote down that this is 1/3. So I'm going to look at the sides of these two triangles. I have 1/3 over 1/3. That's opposite that, and vertically opposite is that, over X is equal to this piece here, which we saw to be X minus 1/3. X minus 1/3 over this. And we saw that this is 1 minus X. So there it is. In the most unusual way, you got your equation involving X. Right. It took a long time to get there. And now you can cross multiply and so on, and you see that X is equal to 1 over square root of 3. Okay, so there's a lot of geometry here, regular hexagon and similar triangles and so on. Although the problem itself looks quite simple, very simply stated. The original picture was this. Look how many other things we had to draw to eventually get the value of this x. We had to complete some rectangles, use some parallel lines, similar triangles, and so on. So that is you can see right at the end, x is equal to 1 over the square root of 3.